Titan is a supercomputer built by Cray at Oak Ridge National Laboratory for use in a variety of science projects. Titan is an upgrade of Jaguar, a previous supercomputer at Oak Ridge, to use graphics processing units in addition to conventional central processing units, and is the first such hybrid to perform over 10 petaflops. The upgrade began in October 2011, commenced stability testing in October 2012, and it became partially available to researchers in early 2013. The initial cost of the upgrade was $60 million, funded primarily by the United States Department of Energy. Titan has AMD Opteron CPUs in conjunction with NVIDIA Tesla GPUs to improve energy efficiency while providing an order of magnitude increase in computational power over Jaguar. It uses 18,688 CPUs paired with an equal number of GPUs to perform at a theoretical peak of 27 petaflops. However, in the LINPACK benchmark used to rank supercomputer speed, it performed at 17.59 petaflops. This was enough to take first place in the November 2012 list by the 500 Tongan Pingus organization. Titan is available for any purpose. However, selection for time on the computer depends on the importance of the project and its potential to fully utilize the hybrid architecture. Any selected code must also be executable on other supercomputers to avoid dependence solely on Titan. 6 Vanguard codes were selected to be the first to run on Titan, dealing mostly with molecular scale physics or climate models, while 25 others are also queued for use of the machine due to the inclusion of GPUs. Programmers have had to alter their existing code to properly address the new architecture. The modifications often require a greater degree of parallelism as the GPUs can handle many more threads simultaneously than CPUs, and the changes often yield greater performance even on APU-only machines.
Supercomputing has become an indispensable scientific instrument. For 2 decades, Oak Ridge National Laboratory has been committed to providing researchers with the most powerful tools possible.
My main research interests are in more theoretical and computational seismology. So we do imaging. We image the Earth basically on all scales, from hand samples to problems in exploration seismology to imaging the entire planet.
I am a computational biophysicist, which means I'm using computers to solve problems of a biological nature.
The virtual environment for reactor applications, or we call it VERA, is a suite of software tools that model the different physics that occur within a nuclear reactor.
In 2008, ORNL's Jaguar brought working scientific applications to the petascale. In 2012, ORNL is leading the way once again with Titan, the largest system ever to rely on GPU accelerators. By combining the impressive speed and energy efficiency of GPUs with the proven computing capabilities of traditional CPUs, Titan boasts 10 times Jaguar's computing power while drawing essentially the same amount of electricity.
So in this day and age where we can't afford to keep pulling more and more power, this gives us an order of magnitude more peak capability, we hope sustained capability, for the same power consumption.
I think what we will see is that Titan is seen as the first broadly available heterogeneous multi-core architecture. This is absolutely required as we start looking how we're going to get to the exascale computers of the future.
We'll be able to turn around simulations that now take weeks or even months to run in a much shorter amount of time.
One benefit of adding GPUs to the existing CPU architecture is that researchers will be able to use Titan even before they optimize their codes. Titan is among the world's most powerful computing systems, even without the GPUs.
Important thing for the users to understand as we transition from Jaguar to Titan is that all the codes that run on Jaguar today will run essentially unmodified on Titan tomorrow.
So Titan poses interesting challenges for people, for domain scientists. The good thing about Titan is that from day one, it's still a resource that we can continue to utilize. It's not like you must utilize the GPU. So it's a great transitional machine because, one, we can already push our calculations to another level because there are more cores, more memory, as well as the Gemini interconnect will make our calculations more efficient.
But to get the most out of Titan, researchers will have to optimize their applications to take advantage of the GPUs. That is a substantial job.
Understanding what portions of the algorithms are amenable to GPUs is the first step. The next step is making sure your data structures and your algorithms are suitable for performing work on GPUs.
That has been a major undertaking. We've basically dedicated one full person in the group towards developing the GPU version of the software.
So it will require considerable work to exploit that resource, which is why we depend so much on collaboration with computer scientists and applied mathematicians to refigure algorithms that are more efficient on GPUs, as well as learning ways to deal with data management that we've never thought of before.
The effort will have an impressive payoff. With Titan, researchers will have access to unprecedented computational power. That power will allow them to simulate systems with greater detail and accuracy.
What Titan will allow us to do is to look at what happens in the cells of patients, in the entire organism maybe. Until now, we were only able to look at bits and parts of what happens when people are sick.
And so our next goal is to take this to the scale of the entire planet.
We get benefits in terms of the fidelity that we can see in terms of the computational science simulations, because the size has been increased, as well as the time to solution. And both of those things lead to better science.
Whereas in the past, the nuclear industry has typically looked at the different physics behaviors, like the neutron behavior, the fluid flow, the material behavior, separately. A machine like Titan gives us the computational resources to start looking at those physical phenomena in a combined manner, a coupled manner.
In the field of drug discovery, when we want to discover new drugs to treat patients that have difficult to treat conditions, Titan is going to be the equivalent of the Saturn V rocket in the field of space exploration.
And of course, the work done for Titan will be valuable going forward for any accelerated system, which is likely to include all of the world's most powerful machines.
There's I think, a fallacy in HPC that we think you need heroic programming efforts for GPUs.
I'll paraphrase one of our reviewers who said, the lasting legacy of Titan is going to be the codes that we develop and that we transition to this new world of hybrid multi-core processors and hierarchical parallelism.
Titan won't be the end of the road, but it will be a major step on the way to the next milestone. An exascale supercomputer capable of churning through 1,000,000 trillion calculations a second.
Whereas a machine like Titan gives us the ability to start looking at the combined physical phenomena instead of looking at the pieces individually, but looking at them in a coupled manner. We really need several hundred petaflops or even up to the exascale level to really address the time and length scales needed for the challenging safety questions that will arise.
Currently, we typically look at global wave propagation with periods on the order of 27 seconds. So it takes a wave 27 seconds to displace a particle and move it back down. So it's very slow, almost half a minute. So we'd like to push that much shorter. On Titan, we would go to 17 seconds to begin with, but we would very much like to go to 9 seconds, which is sort of a magical cutoff where noise of the Earth induced by oceans and wind starts to become a problem.
With Titan, we're going to be able to look at what happens in the cells and organism of individual patients. With the exascale computing, we're going to be able to address issues of public health, that is, how drugs perform in a population of patients.
Going from Titan to exascale means that we will be able to do petascale or tens of petaflop scale calculations abundantly. And this is a very fundamental step that will make scientific productivity go up.
In the meantime, Titan will be expanding the limits of science.
Because at the end of the day, it's not fielding the #1 machine in the world, it's delivering the science. And so we all need to be excited that we're going to help deliver the nation's best science here at Oak Ridge National Laboratory using modeling and simulation, and using modeling and simulation at scale.